Good morning, everyone. Good morning, Hervé. I'd like to talk about von Neumann's work on biology and my attempts to extend his ideas, which I call metabiology, and or life as evolving software. Now, if you want to see something written on this topic, I don't have foils, but I have a book and a paper on this topic. You can get both of them from my academia website. If you Google Chaitin and academia, it's academia.edu. There's a book there called Philosophical Computations. The subtitle is Reflections on the 50th Anniversary of the Halting Probability. That's a 200-page book. It's actually two books, and there are two chapters on biology in the first part. And there's also a short paper there on my academia website called Metabiology 2.0, which is actually precisely the topic of this talk, Metabiology 2.0. So von Neumann has two fundamental pieces of work. The John von Neumann, the mathematician, this was quite a while ago. He has a talk from, I think it was 1930, I don't remember, it was in the 40s. It's called The General and Logical Theory of Automata. And this is a very deep paper, in my opinion. It talks about natural automata and artificial automata. So an artificial automata is a computer, which was just starting then, and a natural automata is a biological organism. And what this paper is saying is that in both cases, the fundamental mathematical idea is software. It's software that makes computer technology so powerful, and it's software that explains the plasticity of the biosphere. And this is a very profound paper that inspired Sidney Brenner to leave South Africa and go to work with Crick at Cambridge and be one of the founders of molecular biology. It's not as well known as Schrodinger's little book, What is Life? But as Sidney Brenner said, in many ways, it's more profound. And I would agree with Sidney Brenner on that. Then there is a posthumous book by von Neumann, which is called Theory of Self-Reproducing Automata, that has a self-reproducing computer in a cellular automata world, along the lines of the kind of deterministic system on a plane, discrete deterministic system on a plane that Hervé just showed you in his talk, in his lovely talk, by the way. So these are von Neumann's thoughts. So the first one says this fundamental idea is software. DNA is software. And the second one has a toy world, a discrete cellular automata plane divided into squares, in which von Neumann constructs a very complicated self-reproducing automata that copies itself. Okay, so I've attempted to continue in von Neumann's spirit, continue this train of thought. So the first step, and I call this effort metabiology, as I already said. So the first idea is this, going back to von Neumann's paper on the general and logical theory of automata, what I propose in metabiology is, it's a toy model of biology. It's a theoretical biology that instead of studying my goal is to prove theorems. I'm a mathematician, right? Von Neumann was a mathematician. I'm a mathematician. So the goal is biological models where I can prove theorems about the behavior of these models. So the first idea was, well, DNA is a very complicated programming language, and it makes no sense to try to prove theorems mathematically about how DNA will evolve when subject to mutations and selective pressure. It's just too complicated, too difficult, and it's a language that we don't fully understand. So what I propose in metabiology is, instead of attempting to study mathematically the evolution of DNA subject to random mutations and selection, I propose looking at the evolution of computer programs, artificial software, rather than natural software, which is DNA. I have a little book about this that was published, I don't know, 2012 maybe. It's a very simple toy model of evolution, and it has to be very simple so that I can prove some theorems. You know, one has to simplify greatly in order to be able to prove anything. So the model consists of a single organism, which is software. It's a software organism. It's a program, and it's subjected to random mutations, and the mutations are global and they're algorithmic, which is doesn't look too realistic biologically, perhaps, because an algorithmic mutation is chosen at random and applied to a software organism. There's only one software organism, there's no population. And what the mutation does is it's an arbitrary program chosen at random that takes as input the current organism and produces as output a new organism. So these can be global changes to the DNA, to the computer program. Okay, so this is a very simple model, and there's no environment, there's no population, there's a single organism. It's subject to a randomly chosen algorithmic global mutation, and the fitness of the organism is defined to be the aim of the organism is to calculate a very large positive integer, and the bigger the integer, the fitter the organism. So the organisms are mathematicians, and what they want to do is name a very big number as concisely as possible, actually, is what's happening. This is called the busy beaver problem in theoretical computer science. It's equivalent to Turing's halting problem. Okay, so this is a very simple model. So there's no population, there's only a single organism, there's no environment. And if a mutation produces an organism with that's fitter, it replaces the original organism. Otherwise, we keep applying randomly chosen algorithmic mutations to the current organism. So this is a random walk in software space, is what this is. It's actually a hill climbing random walk in software space. And random walks are something that mathematicians feel comfortable with, but this is a random walk in a different space. It's a much richer space. You know, it's not two-dimensional space or three-dimensional space. It's the space of all possible computer programs, software space. And I'm able to prove a few little theorems about the speed of evolution in this simple-minded model, and which is encouraging. That means that the model has been made simple enough that that it's possible to prove some theorems about the speed of evolution. And so this is what I called metabiology, and I have a little book on this, as I said. But you can read about it in Philosophical Computations and in the little paper Metabiology 2.0 on my academia website. Okay, so the new thing that I just realized, actually, it may have been in Paris. There was a birthday party for the Omega number, the 50th birthday of Omega in Paris, at UM6P France in Paris. And this was roughly when I realized that I can make a more realistic model. Now, the more realistic the model is, the harder it is to prove theorems. But this model is not that realistic. What it does is I go from a single organism to a population of organisms, and I do have a geometry, I do have a space in which the organisms are moving around. It's a two-dimensional two-dimensional square tessellation. So the organisms can move around. And let me add that von Neumann's self-reproducing organism can't move around. The only way it can move is by reproducing itself and then reproducing the copy and like that. So what I have is a higher level model than von Neumann. I have a toy world with, it has organisms, it has, they're software organisms, it has mutagens that are also moving around. And the idea is that an organism, it's a higher level model than von Neumann's. Each square in this space, this two-dimensional space, can have an arbitrary software organism. So it can be arbitrarily big. And since the entire organism is considered to be in one square, it is easy for organisms to move around. You can just postulate that an organism can move to an adjacent square with probability 1/4 to move up, down, left, or right. Since the organism is, in this model, it fits in a single cell, a single square cell, it's very easy for it to move from one cell to another. You know, you make the rules when you set up a toy world. And also moving around, in addition to this population of software organisms that can be arbitrarily big programs, you have mutagens, which also occupy one square. And the rules of the game are that if two, you know, there are lots of details, but basically the rules of the game are you populate this infinite two-dimensional plane that is divided up into identical squares. You populate it, you know, with a certain proportion of organisms and a certain proportion of mutagens, and you start them moving around. And the rules are roughly like this. If two organisms collide, you don't let them superimpose, but you let them abut, is, I think, the simplest rule. So if they touch, the idea is that they conjugate. So then the fitter organism will replace the less fit organism. So you will have two copies of the fitter organism then. And if a mutagen abuts with an organism, the organism is subjected to a random algorithmic mutation, just as in the old metabiology. So this is a version of metabiology in which you have a toy world which is two-dimensional, there's space, and you have a population of organisms that are moving around, and you have a population of mutagens that are also moving around. Now, since this is more complicated than the original model, which had only a single organism, it's more difficult to make estimates of the behavior of the system, but I think it is sort of like this is starting to sound, you know, sort of like statistical mechanics. These kind of things, one can make estimates, one can do simulations, one can get a feeling for how the system operates. But of course, the more realistic you make the model, the more difficult it is to characterize, to prove theorems about it. But the basic theorem that the system will evolve relatively quickly by random mutations, that is in Metabiology 1.0, does extend to Metabiology 2.0. That's sort of immediate. So I'm proposing this as a new research direction. And I have to say, it took me a dozen years to realize that there could be a model of life as evolving software that is more realistic than the original model, but at the cost of complicating the estimates of the behavior of the system. So I'm proposing this as a new research direction. And um, I think this is the level at which one has to model evolution mathematically to be able to prove theorems. You know, the game of life that Hervé described to you is too low-level a toy world, and von Neumann's original cellular automata world was also too low-level to be able to prove theorems. So the toy world that I'm proposing, where an organism is where a square can have an arbitrary program, an arbitrary organism, I think is a level, a better level at which to model evolution in order to be able to prove theorems. Okay, so to wrap this up, the idea is this. What I'm thinking about is, I like to call it theoretical physics, because it's the theoretical physics of possible worlds, not this world. So we want to find a possible world that is non-trivial, you know, a possible world where we know the theory of everything, because we set up the rules of how this possible world operates. Conway created the game of life, and Neumann had created his 29-state cellular automata world way before that. And I'm proposing another class of toy worlds. And the criterion for a toy world to be interesting is that you can prove that life evolves. And this toy world that I'm proposing, I believe, satisfies that criterion. So theoretical physics, the idea is that you define a toy world, you know all the rules, you know the theory of everything, and we're interested in toy worlds for which we can prove that life will evolve. And I think I've sort of come up with such a model, but it would be interesting to continue research in this area. So thank you for your time. And as I said, if people want to know more about this, you can go to my academia website, and there is a book, Philosophical Computations, and there is also a short paper called Metabiology 2.0. Thank you very much for your time.
Thank you, Greg. Thank you for this presentation. One or two questions? Yes, please.
Yeah, thank you very much for the great presentation. So I would like to know more about the technical details of the metabiology model you mentioned. I'm not sure if I can. No, okay. So when you apply the busy beaver problem, there's always the issue of undecidability. So I wonder how you deal with that kind of possibility when you have two organisms competing against each other. If one of the programs happen to be undecidable behavior, so how do you deal with this?
Yes, that is a technical complication. The metabiological model has a problem, but it's not computable, because if you apply an arbitrary mutation to a program, there are two things that can go wrong. One possibility is that it gives you a new organism, but this new organism never halts. You know, so it doesn't have a fitness. So that's an invalid organism. And the other problem is that if you apply an arbitrary algorithmic mutation to a software organism, the mutation may never halt. You started running on the organism as input, and it never produces a new organism. So one has to postulate how you don't want to, in this little metabiological toy model, you don't want to assume an oracle for the halting problem in full generality, because that trivializes the whole thing. So you do need an oracle for the halting problem to a certain extent to avoid those two glitches, as you, of course, correctly pointed out. But you have to try to restrict the use of the oracle carefully so that it doesn't collapse the whole thing and trivialize it. And I believe I've done that in the original version. It's a little book called Proving Darwin that talks about this. But you can find the central chapter of that book on my academia website. That's an understandable version. You can also find a detailed technical paper with all the proofs. If you're interested in that. So you are very correct. Your question was right on target.